In the silence between worlds, where the fabric of the cosmos vibrates with ancient energies, there are moments when the universe itself seems to shudder, sending out a brief, fierce cry. These cries are fast radio bursts, enigmatic flashes of radio energy that originate from the farthest reaches of space, their origins shrouded in as much mystery as the dark between the stars. The story of FRBs is one of cosmic riddles, relentless pursuit, and the tantalizing possibility that, in their fleeting signals, we might be hearing echoes of intelligence not our own. It begins, as all great scientific mysteries do, with an accident. In 2007, Duncan Lorimer, an astrophysicist at West Virginia University, along with his student David Narkovich, was combing through old data from the Parkes Observatory in New South Wales, Australia. They were not searching for anything out of the ordinary, merely reviewing pulsar survey data, the celestial heartbeat of neutron stars. But buried in the noise, they found something utterly unexpected, a pulse of radio energy, lasting just 5 milliseconds, so bright it seemed impossible. It had arrived in 2001 but gone unnoticed, a cosmic spark overlooked in the torrent of data that falls ceaselessly upon our planet's radio telescopes. At first, suspicion reigned. The world of radio astronomy is haunted by ghosts, earthly interference masquerading as signals from the stars. Microwave ovens, passing aircraft, satellites, even the observatory's own electronics. All can leave their fingerprints in the data. But this signal, later christened the Lorimer burst, defied those explanations. Its properties matched nothing known to human technology. It was both incredibly brief and, when its dispersion was analyzed, unfathomably distant. The radio waves had been stretched and delayed as they passed through the ionized intergalactic medium, a cosmic mist of free electrons that lies between galaxies. From this dispersion, Lorimer and his colleagues deduced the signal had traveled billions of light years. Whatever had produced it must have unleashed as much energy in a few milliseconds as the sun emits in 30 years. The Parkes telescope, with its broad metal dish and ever-listening ear, had caught a whisper from the deep universe, one so loud, in radio terms, that it bordered on the unbelievable. And then, for years, the universe was silent again. No others appeared. Some doubted the Lorimer burst was real at all. But in 2013, a team led by Dan Thornton at the University of Manchester announced they had found 4 more, each as brief, as bright, as mysterious as the first. They were now called fast radio bursts, or FRBs. The floodgates opened. Astronomers around the world turned their instruments skyward, retrofitting their data processing pipelines and sifting through archives. Soon, dozens more FRBs were found, scattered across the sky, no two alike, none repeating at first. The hunt for their origins began in earnest. Their brevity and brightness suggested cataclysms, the final collapse of a star, the collision of neutron stars, the evaporation of primordial black holes. Each hypothesis bore its own scientific promise and peril. The study of FRBs became a battleground of ideas, with researchers racing to model the unthinkable energies involved, to match the fleeting signals to cosmic events. Yet the FRBs did not yield their secrets easily. In 2015, the first repeating FRB was discovered, FRB 121102, detected again and again from the same region of the sky in the constellation Auriga. This changed everything. If FRBs could repeat, they could not be the death throes of massive stars, nor one-off cosmic collisions. Their source must survive, capable of emitting burst after burst. It was an invitation. The universe was offering us a chance to study these signals, to trace them back to their origin. The Very Large Array in New Mexico, with its sweeping arms of radio dishes, was trained on FRB 121112. After months of observation, its precise location was identified, a dwarf galaxy over 3 billion light-years away. The host galaxy was peculiar, small, star-forming, rich in heavy elements. Within this galaxy, the source of FRB 121102 was nestled in a region of intense star birth, close to a persistent radio source, perhaps a nebula or the remnant of a supernova. Theorists speculated, perhaps a young, highly magnetized neutron star, a magnetar, was to blame. Magnetars, with their colossal magnetic fields, can twist space and time, generating bursts of energy that dwarf anything else in the known universe. Yet, even as models were proposed, the data complicated matters. Some FRBs repeated, others did not. Some were polarized, their radio waves twisted by magnetic fields. Others showed no such signature. The diversity of FRBs suggested a diversity of origins, or a phenomenon so complex it defied simple explanation. The technological race to catch FRBs in real time accelerated. New telescopes like the Canadian Hydrogen Intensity Mapping Experiment, CHIME, in British Columbia, were built with one purpose: to listen all sky all the time. CHIME's array of cylindrical reflectors and thousands of antennas could scan vast swathes of the sky, making it the most prolific FRB hunter yet. In its first year, CHIME detected hundreds, each one a cosmic cipher, each one a new clue. As the catalog grew, patterns emerged. Some FRBs seemed to cluster in time, others arrived in isolation. Some repeated with periodicity, as if governed by a cosmic clock. Others never returned. The energy scales varied, the polarization signatures hinted at environments of staggering violence. Dispersion measures, how much the signal was stretched, offered rough yardsticks to their distance, but the true nature of their sources remained elusive. Amidst this scientific ferment, a question as old as the search for extraterrestrial intelligence began to whisper at the edges of the data. Could some FRBs be artificial? The idea was not new. Since the earliest days of radio astronomy, when Jocelyn Bell Burnell discovered the first pulsars in 1967, astronomers have been wary of signals that seem too regular, too powerful, too strange. The first pulsar was jokingly dubbed LGM-1 for Little Green Men. But FRBs were different. Their energies were orders of magnitude beyond anything human technology could generate, their brevity and brightness unmatched by most natural phenomena. In 2017, Avi Loeb, chair of Harvard's astronomy department, and Manasvi Lingam, then at Harvard, published a provocative paper. They calculated that the energies involved in FRBs were enormous, but not inconceivably so for a sufficiently advanced civilization. They hypothesized that FRBs could, in principle, be leakage from gigantic transmitters, perhaps used to power light sails, vast sheets driven by intense beams of radio energy, carrying spacecraft across interstellar or even intergalactic distances. The numbers, they argued, were not impossible. A planetary-scale array, powered by a star, could generate the necessary pulses. The beams would need to be tightly focused, sweeping across the cosmos, and Earth might be catching only the briefest flash as one such beam crossed our line of sight. The idea was met with skepticism, but not dismissal. For decades, SETI, the search for extraterrestrial intelligence, has operated on the principle that, in the absence of proof, all possibilities must be considered. The challenge, as always, is distinguishing the artificial from the natural. The universe is endlessly inventive. Nature routinely produces phenomena more energetic, more regular, and more bizarre than our most fevered imaginings. In the case of FRBs, the burden of proof is immense. Natural explanations abound: magnetars with their twisted fields and starquakes, neutron star mergers, flaring accretion disks around black holes, cosmic strings snapping in the fabric of spacetime. Each model matches some of the data, none all of it. The periodic repeaters in particular have drawn attention. In 2020, CHIME discovered FRB 18096 Ju158+65, which repeats every 1635 days, like clockwork. Such regularity is rare in astrophysics and invites speculation. Could it be a rotating beacon, a galactic lighthouse, or a natural process we simply do not yet understand? The search for answers drives technological innovation. Instruments like the Australian Square Kilometre Array Pathfinder, ASCAP, and the South African Meerkat Telescope are mapping FRB localizations with increasing precision. The Deep Synoptic Array in California, with its distributed antennas, is designed to capture FRBs in real time and provide near-instant localization. Each new instrument brings us closer to the sources, and each new detection adds to the puzzle. The physics of FRBs is a study in extremes. The brightness temperatures, how hot a source would have to be to emit such intense radio waves, reach quadrillions of degrees, far beyond the surface of any star. The emission mechanisms are likely coherent, meaning the radio waves are emitted in phase, like a laser, rather than as random thermal noise. This points to exotic astrophysical engines, relativistic shocks, magnetic reconnection, or the crustal fractures of magnetars. The environments inferred from the rotation and dispersion of the signals are dense and magnetized, often within star-forming regions or close to supernova remnants. Yet the diversity persists. Some FRBs show complex frequency structures, subbursts sweeping downward in frequency, as if chirped by some cosmic oscillator. Others arrive as single broadband flashes. The repetition rates vary, as do the energy distributions. The local environments differ, some in tiny dwarf galaxies, some in massive spirals, some in the outskirts of galaxies, others near their luminous centers. The data is rich, but the theory is tangled. In 2020, for the first time, an FRB was detected within our own galaxy. On April 28th, the Magnetar SGR 1935+2154, located about 30,000 light-years from Earth, emitted a burst of X-rays and, simultaneously, a radio flash matching the properties of extragalactic FRBs. The Canadian CHIME and the American STARE-2 array caught it independently. This event suggested that at least some FRBs can be generated by magnetars, lending weight to the leading natural explanation. Yet even this did not solve the mystery. The galactic FRB was orders of magnitude less energetic than its extragalactic cousins, and it repeated only once. The puzzle remains. Are all FRBs magnetars, or is nature more diverse? Philosophically, the search for FRBs is a microcosm of our quest to understand the cosmos. We are listening for whispers across the abyss, trying to decode messages written in a language we do not yet speak. The universe is vast, its history long, and our moment in it brief. FRBs remind us of the limits of our knowledge and the boundless reach of our curiosity. Consider the scales involved. A typical FRB detected at a redshift of 0.5 has traveled for 5 billion years. It began its journey before the sun had finished forming, before Earth had cooled, before life had emerged from the primordial seas. The radio waves, stretched and scattered by the intergalactic medium, have traversed clusters of galaxies, cosmic filaments, voids, and the dark matter scaffolding that underpins the universe. By the time they reach Earth, their original signal is distorted, but not erased. In their dispersion, astronomers find not just a measure of distance, but a probe of the cosmic web itself. FRBs are becoming tools for mapping the universe, measuring the density of baryons, the missing ordinary matter that, until recently, eluded detection in the vastness between galaxies. Technologically, the pursuit of FRBs is a story of innovation. The CHIME telescope, with its stationary cylinders and sophisticated digital backend, can process terabytes of data per second. Machine learning algorithms sift through the noise, plucking out candidate bursts in real time. The data rates are so high that for every FRB detected, billions of candidate events are discarded. The challenge is not just to detect, but to localize, pinpointing the host galaxy, identifying the environment, searching for counterparts in other wavelengths. The global collaboration is intense. Observatories on every continent coordinate their searches, sharing data and methods. The International Fast Radio Burst Collaboration convenes regularly, fostering debate, cross-checking results, and refining theories. The field is young but growing rapidly. Papers appear weekly, each new detection spawning fresh hypotheses. The diversity of FRBs continues to provoke. Some bursts, like FRB 180916C J01558+65, show periodic activity, hinting at binary star systems or precessing neutron stars. Others, like FRB 121112, repeat erratically, with hundreds of bursts recorded over months. Some are polarized to extremes, their radio waves twisted into corkscrews by powerful magnetic fields. These signatures offer clues to the environments, perhaps near massive black holes or within the magnetospheres of young neutron stars. The artificiality hypothesis persists at the margins. Critics argue that no natural process could produce such brief, intense, and varied bursts. Proponents counter that the universe is more inventive than we imagine. The SETI community, cautious but intrigued, has begun to monitor FRBs for signs of modulation, patterns or encodings that might betray a technological origin. So far, the signals are noise, bright, brief, and featureless, without the repeating codes or narrowband signatures expected of intentional beacons. Yet, absence of evidence is not evidence of absence. The philosophical implications are profound. If any FRB were to bear the hallmarks of intelligence, structured modulation, repetition, a message, we would have proof that we are not alone. The universe would become a little less silent, and the night sky would shimmer with the knowledge that other minds are watching, listening, sending their own sparks across the void. But even without such proof, the mystery endures. FRBs are a new window into the universe, a reminder that the cosmos is not a static tableau, but a living, changing, eruptive place. They invite us to ask, what else is out there, waiting to be discovered? What other signals are we missing, hidden in the noise, overlooked because they are rare or brief or strange? In this sense, the story of FRBs is the story of science itself. It is a tale of curiosity, skepticism, wonder, and the relentless drive to understand. It is a reminder that the universe is not obligated to make sense to us, but that by listening carefully, we can sometimes catch its whispers. As the search continues, the catalog of FRBs grows. Each new burst is logged, analyzed, cross-checked. Theories rise and fall. Some suggest that the diversity of FRBs points to multiple origins: Magnetars, neutron star mergers, accretion events, or even cosmic strings, hypothetical defects in space-time itself, remnants from the earliest moments after the Big Bang. Others argue for a unifying mechanism, a single engine capable of producing the observed variety. The debate is fierce, the stakes high. The discovery of a local FRB within our own galaxy was a watershed, but it opened as many questions as it answered. If magnetars can produce FRBs, why do some repeat and others not? Why do some bursts show complex frequency structures while others are simple? What determines the energy scale, the polarization, the repetition rate? The technical challenges are formidable. FRBs are unpredictable, brief, and rare. Most are detected after the fact, when the data is already written to disk. Real-time detection and localization are essential for multi-wavelength follow-up, to search for counterparts in X-ray, optical, or gamma-ray bands, to constrain the environments, to catch the source in the act. To this end, new instruments are being built. The Square Kilometre Array, under construction in Australia and South Africa, will be the most sensitive radio telescope ever built, capable of detecting FRBs across the observable universe. Its vast collecting area, digital processing power, and real-time alert system promise to revolutionize the field. The hope is that, with thousands of FRBs detected and localized, patterns will emerge, correlations will be found, and the underlying physics will be revealed. But the allure of the unknown remains. The possibility, however remote, that some FRBs are artificial, the product of alien technology, is a siren song for the imagination. It is not the dominant hypothesis, but it is not dismissed. It cannot be. The universe is vast, ancient, and, as Arthur C. Clarke observed, the two possibilities, that we are alone or that we are not, are equally terrifying. The search for FRBs is thus a search for ourselves, for our place in the cosmos, for the limits of our knowledge, for the reach of our curiosity. It is a reminder that we are part of a universe that is still unfolding, that the story of the stars is not yet finished. In the end, FRBs are both a mystery and a promise. They are cosmic lighthouses, flashing briefly across the darkness, marking the boundaries of our ignorance and the horizon of our hope. They invite us to listen, to wonder, to keep searching. And so, the astronomers continue. Night after night, day after day, their instruments sweep the sky. Their algorithms sift the data. Their minds race ahead of the signals, speculating, modeling, imagining. The FRBs come, brief and brilliant, then are gone. Each one is a message of sorts, a signal that the universe is alive with possibility. The story is not yet finished. The next burst may come tonight, or tomorrow, or 1,000 years from now. It may be natural or artificial, or something stranger still. All we can do is listen and wait and wonder. In the silence between worlds, the universe is speaking. We have only just begun to hear its voice.